August 1943. On a training field near Salisbury Plain, a row of Sherman and Churchill tanks stood motionless under the midday haze. The steel hull shimmered with a faint greenish-grey, their outlines dulled by a thin, uneven coat of new paint. From ground level, it looked like nothing unusual, just another maintenance trial ordered by the Royal Engineers. But several hundred feet above, circling in a reconnaissance Spitfire fitted with a modified infrared camera, the change was unmistakable. On the operator's film roll, the tanks that had once flared white-hot against the soil now merged almost seamlessly with the background. Their thermal signature had dropped by nearly half. Technicians at the airfield compared the negatives against older records, checking densities with optical densitometers and marking the difference in precise millimeters. To the naked eye, the contrast was gone. The experiment had begun months earlier in a small workshop at Farnborough, where Royal Engineers chemists tested pigment suspensions under arc lamps and mercury vapor bulbs. The challenge was clear: Luftwaffe reconnaissance units were now using infrared-sensitive film, the same technology adapted from night fighting optics, to detect Allied armor before dawn offensives. Conventional camouflage paint, based on chromium oxide and standard olive drab, was invisible to visible light but reflected strongly in the near-infrared band. German analysts could read the difference like a map, identifying Allied vehicle parks even under tarpaulins. To counter it, the British needed a coating that would absorb infrared radiation rather than reflect it, a paint that would darken not in shade, but in heat. Early attempts were clumsy. Engineers mixed lampblack, powdered rubber, and ferric oxide into base enamel, only to find it cracked in sunlight or peeled from steel plates after exposure to diesel fumes. A test batch stored at RAF Odiham was dismissed as ridiculous in a 1942 memo: too soft, too costly, too unstable for field service. But one technician, Captain Geoffrey Barclay of the Camouflage Directorate, persisted. He noted that when carbon black was ground with specific manganese oxides in a silicone carrier, the resulting film absorbed a wide band of infrared wavelengths while maintaining adhesion. His samples, baked in an improvised oven beside the hangar, registered surface temperatures 5 to 8 degrees cooler than standard paint when exposed to a 1,000-watt lamp. By 1943, the formula had a name: infrared reflecting paint, Type B. At Larkhill and later in North Africa, batches were applied experimentally to command tanks and armored cars. Each vehicle was divided into panels, half with the new coating, half with the old. Aerial photographs confirmed the effect with almost clinical precision. The difference showed not in color, but in contrast ratios measured on infrared plates. Intelligence officers at the Allied Photographic Interpretation Unit noted that when viewed through German-style filters, the treated panels appeared as featureless as the surrounding soil. Reports forwarded to the U.S. Camouflage Board described the British results as statistically significant and repeatable under multiple humidity and light conditions. From this quiet series of field tests emerged one of the least known yet most effective survivability measures of the war. There were no headlines, no public demonstrations. The innovation was applied quietly, sometimes inconsistently, across divisions in Tunisia and southern Italy, where Luftwaffe reconnaissance flights were still frequent. Tank crews, unaware of the optical science behind their new coating, simply called it the dull paint. But according to reconnaissance analyses from late 1943, the average detection range of camouflaged armor was reduced by nearly 48% under infrared-sensitive film. The success went largely unrecorded outside engineering files and scientific appendices. In workshops, soldiers stirred the thick, tar-like substance with broom handles and spread it over hulls with brushes or rags. It dried slowly, giving off a faint metallic scent of manganese and oil. Under the summer sun, it seemed almost ordinary. Yet above them, in the narrow frames of reconnaissance film, the transformation was total, an army of machines turning nearly invisible to the most advanced eyes of the enemy. By late 1943, the Royal Engineers trials had shifted from isolated tank yards to operational terrain. The Camouflage Directorate required proof under combat conditions, not laboratory control. On the 22nd of October, near Foggia in southern Italy, a detachment of the U.S. 2nd Armored Division participated in joint testing with British observers. Engineers marked off a dry, uneven plain beside the airstrip, half of it coated with conventional olive drab, half with the new infrared-absorbing mixture. A Lockheed F-5 Lightning, equipped with Eastman infrared film type 5424, made successive passes at 6,000 feet. Ground temperature was measured at 38 degrees Celsius. Within minutes of processing the negatives, the results were undeniable. Where the untreated Shermans glowed pale and distinct, the newly painted vehicles merged with the dust patterns, their edges broken by scattered vegetation and heat haze. Only the shadow lines revealed them. The experiment was repeated twice over 3 days, under overcast skies and again at sunset. The pattern held. In a field tent converted to a mobile darkroom, technicians compared film strips by holding them against light boxes. Notes were written in wax pencil directly on the negatives. Type B, Series 3, undetectable at 5,500 feet. Measurements of infrared absorption were made using portable spectrophotometers, many borrowed from civilian research laboratories. The men worked quietly, surrounded by the scent of acetone and the low hum of generators. Barclay's formula, dismissed as unserviceable a year earlier, now produced data that exceeded expectations. The pigment's performance depended on precise dispersion of carbon black, no more than 0.5 microns in size, stabilized by manganese oxide particles that prevented clumping. According to the Farnborough logbook, this structure created a microscopic trap for near-infrared radiation, converting it to heat within the film instead of reflecting it outward. The Americans, intrigued by the results, requested material samples. Within weeks, tins labeled IRR coating Type B were shipped to Fort Belvoir, Virginia, for analysis by the U.S. Camouflage Board. A memorandum dated the 11th of November, 1943 described the paint as remarkably effective in the 700 to 900 nanometer band, with potential to reduce aerial detection of mechanized equipment. In laboratory photographs taken under controlled light, the coated plates registered an average reflectivity of 6%, roughly half that of standard olive drab. Reports circulated through channels connecting the British Ministry of Supply, the Canadian National Research Council, and several American contractors including DuPont and Sherwin-Williams. Each sought to reproduce the pigment balance under different climatic conditions. In the desert testing grounds of Egypt, further trials confirmed another property, the paint's ability to stabilize surface temperature. Standard tank armor under direct sunlight could reach 65 degrees Celsius. With the infrared-absorbing coating, that temperature dropped to approximately 59. It was not a dramatic difference, but sufficient to alter thermal signatures when viewed through German aerial film using Agfa IR plates. Luftwaffe analysts, unaware of the change, began reporting inconsistencies. What had once been reliable armor sightings now showed insufficient tonal contrast for confirmation. According to correspondence preserved in the Royal Engineers Camouflage File 12 for 56B, field officers were instructed to apply the new paint selectively. Command vehicles, artillery tractors, and forward reconnaissance units were prioritized. Supplies remained limited due to the scarcity of fine-grade carbon black and manganese dioxide during wartime production. The compound's viscosity required constant stirring. Left unattended, it hardened into a gelatinous mass. Crews mixed it with petrol to thin it, brushing it on in uneven streaks that, ironically, improved the optical disruption of tank silhouettes. From above, Allied aerial photographers documented the transition with methodical precision. Contact prints were labeled with exact coordinates and film types, compared side by side with infrared and panchromatic imagery. A pattern began to emerge. Units using Type B paint recorded detection rates between 42 and 49% lower than those using standard coatings. These figures were logged in field summaries, sent through the Camouflage Directorate, and eventually forwarded to the Supreme Headquarters Allied Expeditionary Force. Yet the results were treated as technical data, not tactical revelation. The order was simple: continue use where supply permits. No soldier in the field spoke of infrared wavelengths or spectral absorption curves. They knew only that the dull grey-green mixture kept their machines alive a little longer under hostile skies. Mechanics joked that it looked like mud mixed with smoke, but when the Luftwaffe's reconnaissance sorties failed to return with clear evidence of Allied armor concentrations, no one questioned the formula again. The paint, once ridiculed as an overcomplicated scientific experiment, had quietly altered the visual battlefield of Europe. By the beginning of 1944, the infrared camouflage program had moved from experiment to controlled production. The Ministry of Supply established a small-scale manufacturing line within the Royal Engineers Chemical Section at Chislehurst, using modified paint mills acquired from civilian suppliers. Each drum was stamped with batch codes and distributed through ordnance depots in southern England. Laboratory technicians logged every sample with measured reflectance curves, comparing peak absorption between 700 and 950 nanometers. Statistical charts drawn on wax paper showed a consistent decline in reflective index across all samples. The data suggested that even minor impurities, iron filings, silica dust, or lead residues, could distort the infrared response. The formula's success rested entirely on its purity, a difficult standard in wartime industry. According to technical memoranda preserved at Kew, the first mass-produced batch in February 1944 yielded approximately 1,200 gallons. Enough for a single armored brigade. It was assigned to test formations under General Sir Bernard Montgomery's command in preparation for the invasion of France. The field directive was explicit: apply in one uniform coat, not less than 0.004 of an inch thickness, by brush or spray, to upper surfaces only. Inspectors monitored the application process, recording ambient humidity, surface temperature, and drying times. In one file, the handwriting of Captain Barclay remains legible, adhesion satisfactory. Optical performance equivalent to laboratory control. Recommend adoption for forward units. At the same time, the U.S. Camouflage Board was conducting its own verification. In April 1944, at Fort Knox, infrared photographs of M for Shermans coated with the British compound were compared with vehicles painted in standard U.S. Army olive drab No. 9. Measurements from infrared densitometers recorded an average density difference of 0.35 units, corresponding to a 47% reduction in visibility under film type 5427. The report, signed by Colonel John R. Cuthbert, concluded that spectral absorption characteristics demonstrate consistent masking of metallic heat reflectance, suitable for operational deployment pending logistical review. These results reached London through the Joint Technical Liaison Office, confirming the British findings with independent data. The Royal Aircraft Establishment conducted parallel aerial tests using captured German IR-sensitive emulsions, AGFA infrared film and Luftbild 400. By photographing British armour under identical conditions, analysts could determine how the enemy might have seen them. The images showed a stark reversal. The older paints glared with brightness, their thermal contrast visible at over a mile. The new coating produced a uniform grey indistinguishable from the landscape. Tabulated readings indicated that reflectivity had fallen from an average of 0.32 to 0.17 on the logarithmic scale used by photographic interpreters. For reconnaissance officers trained to identify tonal gradients in film emulsions, this was equivalent to erasing the armor from the frame. In May 1944, the results were presented at a joint meeting of British and American camouflage experts at the War Office's technical branch. The discussion, preserved in shorthand minutes, recorded no celebration, only assessment. Satisfactory performance, one line reads, dependent upon strict control of pigment dispersal and carrier composition. The conversation turned to logistics. Could the compound be produced in sufficient quantity before the invasion? The answer was no. Shortages of manganese oxide limited expansion, and the War Office prioritized supplies for radar and electronic applications. Still, enough was manufactured to coat key vehicles of command and engineering units assigned to Operation Overlord. The quantitative data accumulated by that point were undeniable. Across multiple trials, the average reduction in infrared reflectivity hovered near 50%. In field reports compiled by the Allied Photographic Interpretation Unit, detection rates of camouflaged equipment dropped proportionally with the measured optical density. Graphs traced on transparent film overlays aligned almost perfectly between laboratories in Farnborough and Fort Knox. It was, by scientific standards, a verified outcome, a chemical solution producing measurable operational benefit. Yet official documentation avoided dramatic phrasing. The Camouflage Directorate's final pre-invasion summary described the paint simply as a modification of standard coating yielding superior absorption in the infrared region. There was no mention of invisibility, deception, or advantage, only numbers, ratios, and curves. To the engineers, this restraint was deliberate. Theirs was a craft of measurement, not myth. The paint's efficacy would be judged not by rhetoric but by absence, by what failed to appear on enemy reconnaissance film. By June 1944, when Allied columns assembled along the southern coast of England, many of the vehicles that would roll onto the beaches of Normandy bore a dull, uneven sheen that caught neither sun nor lens. It was a surface that neither glowed nor glimmered, a layer born from chemistry and persistence. The data, archived in faded ink and perforated edges of wartime paper, confirmed what could not be seen, that a ridiculous experiment had become, through precision and quiet endurance, an invisible shield beneath the eyes of the enemy. In the weeks following the Normandy landings, the infrared-absorbing paint vanished into the routine of war. No formal citations, no field awards, no public acknowledgement followed. The compound's production ceased by autumn 1944 as the Allied advance accelerated across France, and priorities shifted toward mobility, fuel, and logistics. Yet within technical circles, quiet correspondence continued. Analysts from the Royal Aircraft Establishment compared post-invasion aerial reconnaissance data, noting that Luftwaffe film captures from June through August showed a marked decline in verified armored concentrations. Of 412 photographs examined, fewer than a third yielded usable detection of British or American armor, even when exposure and angle were favorable. A handwritten comment in the margin of one report read simply, "Coating effective, enemy unaware." By 1945, as the war drew to a close, the scientific findings were compiled into an internal document titled Spectral Reflection Characteristics of Military Coatings. It outlined every stage of development, from Barclay's first improvised pigment tests to the spectral graphs drawn under blackout lamps at Farnborough. The data were presented without commentary, a chain of numbers connecting color to survival. The final table listed mean reflectivity, measured at 0.17 for Type B paint against 0.31 for standard finish. Beside it, an understated notation, operational detection reduced accordingly. The phrasing echoed the restraint that defined the entire program. In the same year, captured German archives revealed that Luftwaffe analysts had indeed observed anomalies in their reconnaissance imagery during 1944. Reports from Fliegeraufklärung units mentioned diminished contrast anomalies on Allied equipment, initially attributed to film degradation or atmospheric haze. None suspected a deliberate countermeasure. In one surviving German memo dated September 1944, the analyst wrote, "Visibility of Allied tanks in near-IR spectrum inconsistent, further calibration required." The deception had worked not through illusion but through physics, concealed within the ordinary appearance of mud-colored steel. After the war, fragments of the research resurfaced in civilian science. The spectral analysis techniques refined for camouflage became foundational to studies in heat-resistant coatings and early thermal control systems for aviation. At Farnborough, former Camouflage Directorate members were reassigned to post-war research divisions working on high-altitude flight and missile guidance optics. Their wartime experience with infrared absorption translated directly into the reflective paints later used on early jet fuselages and radar housings. The lineage between a field-applied tank coating and the thermal control systems of the jet age existed only in data tables, but the connection was exact. Captain Geoffrey Barclay retired from service in 1946. His name appears briefly in the Royal Engineers personnel records, annotated with the phrased chemical camouflage section, special duties. In an interview decades later, he described the project not as invention but persistence. It was only pigment and solvent. What mattered was measuring what the eye could not see. That sentence, quiet and empirical, reflected the spirit of the work. In a war often defined by spectacle, this achievement existed almost entirely in the negative, in what remained unseen. The infrared-absorbing paint never became a headline or a classified legend. It remained a laboratory curiosity, filed under minor technical developments in post-war reports. Yet its results endured in numbers, in the photometric readings archived in folders marked confidential, 1944. The success was not a story of genius but of method. Engineers and chemists followed a problem to its limit, measured its outcomes, and proved a principle that would shape decades of optical science. In the silent sequence of reconnaissance film stored at the Imperial War Museum, the evidence remains. Rows of tanks parked along hedgerows appear faint, then fade entirely into the grain of the landscape. To the analyst of that era, trained to spot the gleam of armor through infrared contrast, these images showed nothing. The void itself became proof. What began as a ridiculous paint mixture, dismissed as impractical, unstable, unworthy of field use, ended as an invisible solution recorded only in spectral data. Its triumph was never seen in motion, never paraded or photographed. It existed in subtraction, in absence, in the narrow band between light and heat where visibility once betrayed survival. By 1947, the scientific community began reclaiming the wartime research that had remained buried in military files. The Ministry of Supply declassified portions of the infrared camouflage studies for internal industrial use, forwarding select documents to British paint manufacturers and research laboratories. Among these were the infraoptical absorption curves for carbon manganese coatings, an unassuming dossier containing spectral plots drawn by hand in faint graphite lines. In technical journals, the language shifted from concealment to efficiency, thermal regulation, solar absorptivity, infrared stability. The same physics that had hidden tanks from reconnaissance film now promised to protect aircraft, pipelines, and observatories from heat distortion. What had been a secret born of necessity evolved into a science of control. In the United States, the U.S. Camouflage Board's wartime findings merged with post-war research under the National Advisory Committee for Aeronautics, NACA. Engineers studying high-speed flight recognized the military coating's unusual thermal properties. Manganese oxide dispersed in carbon matrices absorbed infrared radiation while maintaining consistent surface emissivity, preventing overheating of metal skins exposed to rapid air compression. By the early 1950s, these principles directly informed the heat-resistant paints used on prototype jet engines and early rocket casings. The link to Barclay's work remained undocumented, but his formula's spectral profile, peaking at 880 nanometers, appeared nearly identical in later NACA data sheets. Across the Atlantic, British laboratories continued refining the technique under new terminology, low emissivity coatings, and radiation control films. The Camouflage Directorate's wartime lineage dissolved into the structure of the Royal Aircraft Establishment and, later, into the Civilian Research Council's departments of optical physics. Scientists once engaged in secrecy now published openly in journals like Proceedings of the Physical Society and Journal of Applied Chemistry. Their graphs and constants bore familiar shapes, the smooth decay curves of infrared reflectance that had once determined life or death beneath reconnaissance planes. In the archives of Farnborough, a single report from 1948 captures the quiet transition between war and science. It describes a study on solar heat control for aircraft fuselages, citing previous military investigations into pigment composition for spectral absorption. The reference points back, without explicit mention, to the infrared tank paint. The tone remains unemotional, the method empirical. Yet between the lines lies continuity, a direct inheritance from the engineers who once mixed pigment and oil in tin drums beside the Wiltshire fields. The post-war scientific establishment absorbed their work without ceremony. Barclay himself was never cited in published literature, but his notebook circulated among research teams working on post-war jet camouflage and early radar absorption. In 1953, an internal memorandum from the Ministry of Supply referenced Type B derivative coatings applicable to radar reflection minimization. Within a decade, this idea would evolve into what became known as low observable surface technology, decades before the term stealth entered military vocabulary. Meanwhile, within academic chemistry, the infrared absorption mechanism pioneered during the war became a textbook example of functional pigment engineering. Students learned how particle size and oxide dispersion altered spectral properties, how roughness and binder viscosity determined reflectance. Few were aware that the case study originated from an improvised wartime defense project. The British tendency toward understatement ensured the discovery remained anonymous, its military origin disguised by scientific neutrality. In the 1960s, as satellite imaging and thermal sensors matured, historians and engineers revisiting wartime infrared research recognized its sophistication. Reports once considered peripheral were re-evaluated as foundational to modern optical engineering. The very data that described tank coatings under field lamps became reference points for designing spacecraft insulation and infrared telescope filters. A classified Royal Aircraft Establishment retrospective in 1964 called the wartime coatings the first verified case of large-scale operational spectral adaptation. The phrase was technical yet reverent, a recognition that innovation had emerged not from theoretical foresight but from observation and persistence. By then, Barclay's paint existed only in a few aging tin stored in museum basements, their contents hardened into metallic sediment. Yet the idea it embodied, the manipulation of light beyond sight, had grown into a permanent branch of applied science. It was no longer camouflage but control, the measured adjustment of how matter interacts with radiation. The same spectrum once used to detect and destroy had become the medium through which machines survived in the stratosphere and beyond. And still, within the footnotes of post-war reports, the original phrasing remained, a mixture once considered impractical, yielding measurable reduction in infrared reflectivity. The understatement preserved the tone of its origin, precise, factual, and almost indifferent. But behind those words was a lineage of field experiments, film analyses, and spectral graphs that stretched from Wiltshire grasslands to the metal skin of the jet age. The invisible protection that once saved tanks from the eye of the Luftwaffe had become part of the invisible foundation of modern engineering. By the early 1970s, the archives of wartime camouflage research were being digitized, their brittle carbon copies and fading negatives transferred to microfilm under the supervision of the Royal Aircraft Establishment. In this quiet administrative act, the story of a paint once mixed in field drums found its second life as data. Technicians wearing cotton gloves scrolled through reels of infrared absorption curves and exposure charts, unaware that they were handling the groundwork for a modern scientific discipline. What had begun as an urgent wartime improvisation now read like a technical manual for optical physics. At the Defense Science Laboratory in Porton Down, scientists began revisiting these documents to understand how spectral control could be extended beyond the near-infrared. Their interest was not concealment but calibration, how surfaces could manage radiation across multiple wavelengths to regulate temperature or reduce glare for sensitive sensors. The same equations Barclay's team had used to minimize detection now helped engineers reduce electronic interference and improve the performance of heat-seeking guidance systems. The transition from survival to precision marked the evolution of military science itself. In declassified correspondence between Porton Down and the U.S. Air Force Cambridge Research Laboratories, dated 1972, British physicists referenced wartime manganese carbon coatings as spectral precursors of adaptive emissive surfaces. The term signaled a conceptual shift. The wartime paint, once designed to vanish, had become a prototype for materials that could dynamically manage how they were seen. Engineers began experimenting with layered films, metal oxides, conductive polymers, micro-thin carbon composites that mimicked the same absorption profile discovered on Salisbury Plain 30 years earlier. Meanwhile, the field of remote sensing, born from wartime aerial reconnaissance, evolved into a global scientific enterprise. Satellites like Landsat, launched in 1972, captured Earth's surface in infrared bands that were once the domain of military secrecy. The calibration targets used to align those sensors included specially coated panels derived from the same pigment technology the Royal Engineers had pioneered. In the data streams of environmental observation, the legacy of Barclay's ridiculous mixture persisted in the background calibration of every image. Within British industry, companies such as Courtaulds and Imperial Chemical Industries adapted the spectral principles for civilian use. Infrared-absorbing paints became common in architecture and manufacturing, marketed under phrases like solar heat control coatings and thermal reduction finishes. Their brochures carried no hint of origin, but the patent diagrams revealed familiar structures, carbon black stabilized by transition metal oxides within a silicone carrier. A war-born formula had become a consumer product, its lineage obscured by corporate branding. At the same time, in universities, researchers studying environmental optics and energy conservation rediscovered the same equations first written in wartime laboratories. The physics of emissivity, absorptivity, and reflectance, once used to conceal tanks, was now taught to manage climate and energy. Journal articles that analyzed the balance of radiation across building materials cited earlier British research without realizing it traced back to a secret program of 1943. History had been absorbed into science so completely that its military roots vanished into equations. Among the surviving scientists of the Camouflage Directorate, few spoke publicly of their work. Most retired without recognition. Barclay's colleague, Lieutenant Robert Meacham, who had photographed the original Salisbury trials, wrote a brief letter to the Journal of the Royal Engineers in 1975, acknowledging early experiments in non-visible spectrum camouflage which later found use in thermal control. It was the only public mention of the program before his death 2 years later. The letter ended with a single factual line: the principle remains sound. In the following decade, when defense research shifted towards stealth aircraft and radar-absorbent materials, engineers revisited infrared suppression once more. Declassified internal studies by British Aerospace and the Royal Aircraft Establishment explicitly referenced historical methods of spectral minimization developed during the Second World War. The chain of inheritance, though fragmented, was now recognized. The same spectral graphs drawn in field notebooks with ruler and pencil reappeared, digitized, in the design schematics of composite jet coatings. What began as a wartime necessity, an improvised attempt to vanish from a camera's invisible gaze, had matured into an unbroken continuum of knowledge. It had crossed decades, transformed purpose, and changed vocabulary, yet retained its essential function, to shape how matter interacts with light. The paint that once dulled the gleam of Allied armor had become a principle underlying the modern world's understanding of visibility itself. The spectrum that once betrayed the presence of a tank now defined the sensitivity of telescopes, sensors, and satellites. In laboratories illuminated by cold fluorescent light, scientists still traced curves on screens that looked much like those drawn in graphite in 1943. They spoke of emissivity coefficients and spectral responses, not of battlefields or reconnaissance. But the shapes of those graphs, soft slopes descending toward invisibility, carried within them the same logic born under the shadow of war, that to survive, one must learn not how to shine, but how to disappear.